First of all, many thanks to Booker for the kind invitation and the possibility to share some of the work that we have been recently doing in my group on amorphous carbon coatings. So again, I'm an associate professor at the University of Texas at Austin, and today I will show a couple of applications of our macroscale thermometer from Booker as well. So for those of you who are not familiar with the term diamond-like carbon, this term refers to a broad range of materials which are usually consist of an amorphous carbon network. The usual way of representing these materials is through the so-called pseudo-ternary phase diagram, which you see on the right-hand side of this slide. At the corner of the ternary phase diagram, we will see sp2 carbon, as in graphite, sp3 carbon, as in diamond, and hydrogen. Depending on the deposition methods and the deposition condition, you can achieve different structures and different compositions. You can achieve hydrogen-free amorphous carbon, which is usually referred to as tetrahedral amorphous carbon, or TAC, or hydrogenated versions, such as ACH or hydrogenated amorphous carbon. So the hydrogen content usually goes well below 1 atomic percent up to 60 atomic percent. And sp2, sp3 content can again be tuned by changing the deposition methods and conditions. This has allowed researchers to obtain a wide range of structure and composition, which allowed us to tailor the physical, chemical, and mechanical properties. Because of the tunability of the physical, chemical, and mechanical properties, DLC materials have been successfully used in a range of applications, including as wear-resistant coatings for automotive components such as gears and camshafts, as well as coatings for machining tools, as well as ultra-thin film for hard disk drives. Because of the biocompatibility and bioinertness of DLC, these materials have also been used for joint implants and other applications. And finally, because of the low friction coefficient and friction response of these materials in vacuum, they have also been used and applied in aerospace components. Despite the successful use and potential application of DLCs in a wide range of fields, some limitations have drastically hindered the further application of DLC in an even wider range of fields. The two major limitations are related to the limited thermal stability of DLC and the environmental dependence of the tribological properties. Today, I will mainly focus on the second one. Here you see probably the first work on this topic, where the coefficient of friction is plotted as a function of water partial pressure, or in other words, relative humidity, for two kinds of DLC. The first one is an hydrogenated amorphous carbon. The second one is actually not amorphous, it's a nanocrystalline diamond film, but similar results were obtained also with TAC, or tetrahedral amorphous carbon. Here you see that the coefficient of friction which is the ratio between the friction force and the applied normal load, is very low in inert or low relative humidity environment for hydrogenated amorphous carbon, and progressively increase as you increase the water partial pressure. The opposite is true for hydrogen-free UNCD or amorphous carbon. So what do we know about this dependence? So since this is a critical issue for a number of applications, several researchers have tried to gain insights into the underpinning phenomenon. In this slide, I very briefly summarize more than 2 decades of research. But basically, our understanding on the topic has led us to have a general consensus on the origin of the low coefficient of friction for hydrogen containing AC, so amorphous carbon, at low relative humidity or in inert environment. In this case, the low coefficient of friction was attributed or is attributed to the formation of a carbon-rich layer on the counter surface, so the sliding pin, which results in very weak van der Waals interaction between the transfer layer and the hydrogen-terminated surface of ACH. In other words, in this case, the velocity accommodation mode is interfacial sliding, and which results in a very small and low interfacial shear strength. When we introduce water in the environment, due to the dissociative absorption of water, the oxygen concentration in the near surface region increases, which has been shown by several researchers to lead to an increase in interfacial shear strength, or in other words, the friction response. In the case of hydrogen-free films, such as UNCD or even tetrahedral amorphous carbon, the high friction observed in inert environment or low relative humidity values has been shown to be due to the removal of participating species from the film, such as hydrogen, with the subsequent rapid formation of strong covalent carbon-carbon bonds across the sliding interface. And this has been nicely shown by molecular dynamic simulation by Judith Harrison and others in the community. The reduction in coefficient of friction as the water partial pressure increases has been shown or has been proposed by different people to potentially be due to two completely different mechanisms. The first one has been shown to be due to the passivation of dalgene bonds on the surface by water molecule and oxygen molecules, which prevents the formation of strong covalent carbon-carbon bonds at the interface. But other researchers have shown that this occurs together with the rehybridization of carbon atoms from sp3 to sp2, and in some cases, people have shown also the formation of ordered structure. These two proposed mechanisms have resulted in some friction in the community. I will not go into that topic today, but for sure, from an engineering application, you can see that still we have coatings that have completely relative humidity dependence of the friction response. From really an engineering standpoint, it's not super important sometimes to have an incredibly low coefficient of friction, but it's very critical to have a coefficient of friction that is, or a friction response that is consistent across different environmental conditions. For example, in aerospace applications, where aircraft or space components have to function both in environments that are at very high relative humidity and in environments that are either in vacuum or low relative humidities. To overcome these issues, doping and alloying DLC have been shown to be a very effective way to boost existing properties or impart new ones. DLCs have been doped and alloyed with several different elements, including metals or metalloids such as silicon. And today, in the first part of my talk, I will mainly focus on doping DLC with silicon and oxygen, which has been shown to increase the thermal stability and render the tribological response less dependent on the environmental condition. In the second part of my talk, I'm going to explore rare earth element as a novel alloying element for DLC. This leads to the outline of my talk. In the first part of my talk, I will focus on the effect of alloying elements on and tribological induced changes in surface termination on the resistance of DLC to biomolecule absorption. This is relevant for biomedical application. And in the second part of my talk, I will try to address the limitation of low hydrogen content amorphous carbon, which you have seen to be still a very high coefficient of friction in high relative humidity, by doping amorphous carbon with two rare earth elements, europium and gadolinium. And this work were recently published in carbon and ACS applied material interfaces. So let me start with the first talk. So in this case, we collaborated with Southwest Research Institute in San Antonio